In this video, we're going to be looking at the second part of topic 2A, atomic structure. So we previously covered mass spectrometry, and this is part of the IAS chemistry course from Edexcel. So we're going to be looking at things like ionization energy, how we actually arrange electrons in an atom, how the ionization energies are affected by the electron arrangement, the shapes of the different orbitals that exist, and how we can actually write out the electronic configuration using something known as SPD notation. So in GCSE, you learned that an atom has electron shells, and you learned that the electrons were arranged in specific shells around the atom. You learned that the first shell, which is the closest to the nucleus, can hold a maximum of 2 electrons. The second shell can hold a maximum of 8, and the third shell also holds a maximum of 8. Now, the problem then arises when we get to A level is that this model does not explain how the atoms arrange electrons when we look at any element with an atomic number above 20. So we're going to be moving on from the first 20, and we're going to be looking at now the first 36 elements, so up to krypton. So electrons exist in well-defined energy levels known as quantum shells. So now we're not going to necessarily be using the term energy levels, we're going to be using quantum shells. And all electrons in a quantum shell have similar, but not identical, energies. So every single electron in a quantum shell has a specific energy, and if they're in the same shell, it tends to be similar. Each quantum shell, apart from the first one because it's very small, is then further divided into subshells of slightly different energy levels. So imagine that we have a school that is then divided into classrooms. That's the way that this works with quantum shells. The higher the energy of a shell, the more subshells it contains. Okay, and we're going to look at what that means in a little bit more detail. So the 4 subshells that can exist are known as the S, the P, the D, and the F subshells. Now the S orbital is the lowest energy in each shell, followed by the P, then D, and then F. And you can see that when we have the first quantum shell, or the first energy level, we only contain 1 subshell, which is the S. When we have the second quantum shell, we can contain 2 because it's slightly larger. The third will contain 3, and the fourth will contain 4. Quantum shells 5, 6, and 7 will also contain these 4 subshells, just larger. Now, you're not required to know much about the F subshell, just simply that it exists and how many electrons it can hold. And we will discuss more about the D subshell later on in A level. We're going to put most of our focus on the S and the P at the moment. Now, within each subshell, we can get an area that is then occupied by the electrons, and these areas are known as orbitals. And each orbital can hold 2 electrons, and we'll go into a bit more detail about how these electrons are filled in a couple of slides. So if we go back to our school analogy, so we had our school that was filled with classrooms, and these classrooms now are filled with desks that will have students at them. And this is then the same as having our quantum shells as our school, our classrooms are our subshells, our desks are our orbitals, and the students are our electrons. Now, these orbitals do not have a defined edge that tells us the shape. We just simply have this area of electron density, which just means an area of negative charge, and it just becomes weaker and tails off more and more the further away you move from where the electrons are. But what we can do is we can calculate the surface that's going to contain the majority, about 95% of this negative charge or electron density, and it then tells us the shape of the orbital. And you need to be able to know the shapes of the S and the P orbitals because you can be asked to draw these in an exam. But don't worry, they are very, very simple. So let's start off by looking at the s orbitals. So we've already said that the s orbitals are the lowest energy subshell in each quantum shell. And when we're writing out what orbital we're talking about, we put the number of the quantum shell in front of it, then the letter, either S, P, D, or F. So when we're looking at the 1s orbital, we can see that it is a symmetrical sphere. The 2s is the same shape, just larger. And this is then the same for the 3s, the 4s, the 5, the 6, and the 7. They are all this symmetrical sphere shape, but they just simply get larger and larger as you go down the quantum shells. Now, when we move into the second quantum shell, it will contain an s orbital, so we have 2s, but it will also contain p orbitals. And it actually contains 3 separate p orbitals within this subshell. And these have this dumbbell shape or an infinity sign shape. And they lie along the axis in 3D space. So we have one that lies along the x-axis, known as px, one that lies along the y, known as py, and one that lies along the z, known as pz. Now, when we move into the third quantum shell, we've got a 3s subshell, a 3p subshell, and a 3d subshell. So the 3s and the 3p will be the same shapes that we've already met, just slightly larger, but the 3d now consists of 5 separate d orbitals. And these have slightly more complicated shapes. And we give them these names. So dx squared minus y squared, dz squared, dxy, dxz, and dyz. You will be glad to know that you are not required to know the shapes or be able to draw these for either AS or A2 level, but I'm going to show you what they look like so that you can see. So you can see that we've got a slightly different shape now. They lie along 2 axes. So the dxy, for example, is going to lie along the x and the y axis in 3D space, whereas the dxz would be the x and the z. Now, due to the presence of these subshells that contain in each of these quantum shells, the maximum number of electrons that a shell can hold is now different to what you've learned in GCSE. So what we're doing is just expanding your knowledge slightly. So in the S subshell, we have 1 orbital, and that 1 orbital can hold 2 electrons. In the P subshell, we have 3 orbitals, and each orbital, as we've said, can hold 2 electrons. So if I have 3 of them, I can hold 6 in a P subshell. A D subshell has 5 orbitals, so I can hold 10 electrons, and an F has 7 orbitals, so I can hold 14. Now we can convert that into looking at our quantum shells. Now you learned that energy level 1 holds 2. Now that is still the same. And the energy level 2 holds 8 electrons. Now we know this to be true because it contains an S and a P subshell. Now the difference comes in when we're looking at quantum shell 3 or at the third energy level. This can have an S subshell, a P subshell, and a D subshell. So it can hold now a total of 18 electrons. And from energy level 4 and above, it can hold 32 electrons. Now, as I said, don't worry too much about the F orbitals just now. What we're going to be focusing on is just the first 3 quantum shells. Now, each quantum shell is then split into the specific subshells, and these subshells that exist have an effect on how the electrons are entered into the orbital. So now it's not as simple as simply drawing a target diagram and doing 1, 2, 3, 4, 5, 6, 7, 8. That's a GCSE answer. We're no longer going to be accepting that at A level. At A level, we are now going to be talking about how they fill the specific orbitals. So remember, it's the quantum shell, the subshell, and the orbitals. So the electronic configuration of an atom of any specific element is the distribution of the electrons amongst these atomic orbitals. Now, you learned back in GCSE, for example, if you had aluminium, which has 13 electrons, you would have learned it's 2, 8, 3. And that's saying that in the first energy level there was 2, and the second there was 8, and then the third there was 3. Now what we want to do is we want to go into more detail to show what electrons appear in the S, the P, the D, and the F notation. Sorry, the S, the P, D, and F orbitals. And we call this S and P notation, or sometimes it's written as SPDF notation. And this shows how many electrons are in each orbital for every subshell that's filled. So basically we're taking this 283 and we are expanding it. So if we use aluminium as our same example, in the first shell, it is made up only of s orbitals. So that would have 2 electrons in the first shell and the s orbitals. So we've got the shell, the subshell, and then the electrons. When we get to the second energy level, we've got 8 electrons in total, but we know that because it's in quantum shell 2, it contains s orbitals and p orbitals. So now we write it as 2 electrons fill the 2s orbital, and 6 electrons fill the 2p orbitals. For the third shell, again, we split the 3 electrons across the orbitals. We always fill the s first. So we have 3s2 and then 3p1. And in the textbook, you can see the table on page 50 shows the arrangement of the first 36 elements. You are going to be required to be able to memorize and replicate these in an exam. So we're going to go through the 3 main rules for filling electron shells. So you'll have met some of these in some way in GCSE, you just didn't know that you had met them. So the first rule is known as the Aufbau principle. And this states that the electrons are added to the lowest energy orbitals until all the electrons are accommodated. And this simply means you start with the 1s, then you move to the 2s, then the 2p, then the 3s, and so on and so on. Now, unfortunately, there is some exceptions to this rule, but we will discuss those later. For the moment, we just want to be keeping in mind that we start at the lowest energy level with the lowest orbitals and the lowest subshells, and we work our way up until we run out of electrons. The second rule is known as Hund's rule, and this is something that you learned back in GCSE, and it basically states that electrons will occupy the orbitals singly or on their own until there's no more space, and then pairing has to take place. So we actually learned this when you were drawing out your target diagrams. You were always taught to do 1, 2, 3, 4, and then start pairing. This is a variation of Hund's rule. So this shouldn't be that new to you. This should be something that you feel comfortable with already. And then the third and final rule is known as the Pauli exclusion principle. And this says that 2 electrons cannot occupy the same orbital unless they have opposite spins. Now that sounds a little bit confusing, but it's actually much easier than it sounds. Basically, when we put the electrons in, we will have one that will spin up the way and spin in a clockwise direction. And then we will have one that we will point down the way because it spins in an anti-clockwise direction. You're not required to go into a lot of detail about this. What you need to know and what the Pauli exclusion principle is looking for you to do is to make sure that you have one arrow pointing up and one arrow pointing down. So we use these rules to show us how we can fill the P and the D subshells. So for example, if we look at the arrangements for oxygen, fluorine, and neon. Oxygen has got an atomic number of 8, fluorine is 9, and neon is 10. So what we do is we start at the lowest energy level and we draw one arrow up and one arrow down, and now that has filled the 1s. I now move to the 2s. I put one arrow up and one arrow down. That orbital is now full. Now the 2p we know has got 3 separate orbitals. So sometimes you may see them drawn separately, or you may see it drawn as one large box split into 3. And we fill the electrons individually. So there's 1, 2, 3. That gives me 7 electrons in total that I have filled. So now I have to pair it up with one of my p orbitals, and then I get the notation that we see here. For fluorine, it has 1 extra electron, so it pairs up in the second p orbital, and neon, all of them are paired, noticing that we have 1 arrow pointing up and 1 arrow pointing down. Now, of course, it would not be chemistry unless we had exceptions to the rules, and the exception comes when we're looking at the Aufbau principle. So the Aufbau principle said that we fill the electrons from the lowest energy and we work our way up. And that would assume that we fill all of 1, then all of 2, then 3, and then 4. The problem is when we look at the 3d and the 4s orbitals. In actual fact, the 4s is slightly lower energy than the 3d. So our Aufbau principle takes a bit of a hit, and now we fill it. We do 1s, then 2, then 2p, 3s, 3p, and then we jump to the 4s before coming back to the 3d. Now, this is the only exception that you have to note. You just need to remember that you fill the 4s orbital with its 2 possible electrons before you start to fill the 3d. The 3d orbital is what makes up the transition metals, and we will talk lots about them in topic 17 of A2, and we will look at a couple of examples here as well. So when we look at potassium and calcium, there are atomic numbers 19 and 20. What we would expect if we followed the Aufbau principle to a T is that we would fill the 1s all the way up to the 3p, and then that 1 electron would go into the 3d. Now we know, because of what we've just said, that the 4s is actually lower in energy than the 3d, so we fill the 4s first. So potassium is going to have this 4s1. Calcium is then going to have 4s2, and scandium, which is atomic number 21, will be the first to contain a d electron. And that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So it would be the first to contain this d electron. Now, sticking with the d orbitals, we also have an exception when we have chromium and copper, when we have atomic numbers 24 and 29. So again, it is expected that we would fill the 1s through to the 3p, and that stays exactly the same. Now, based on the rule that we've just said, we would expect to fill the 4s completely first, and then put the remaining electrons into the 3d. Now, for copper and chromium, we actually don't do this. What we do is we promote one of the electrons from the 4s, and it goes into the 3d. So we have 4s1, 3d5. And we get the same with the copper. We would expect it to be 4s2, 3d9, but actually it's 4s1, 3d10. So we should never have 3d orbitals that contain 4 electrons or 9 electrons. That does not happen. We always promote 1 electron up from the 4s. Now you may be asking why. So the reason that we do this is because if we have exactly half full or a full D subshell, it gives it a level of stability. So copper and chromium at first looks like it's unexpected, that why would it possibly want to have this 3d5 and 3d10 electronic configuration, but because it gives this extra stability, we can promote this 4s electron up to the 3d to give us this half full subshell and full subshell, because we get this increased stability. Okay. Now, this doesn't come up very often in terms of actually explaining the reasons why. What it does come up in a lot is writing out the SPDF notation. So please be aware that copper and chromium are exceptions, and they are very common exam questions. Now we're going to move on to talk about something called ionization energy. So ionization energy, and this is a definition that you're going to have to memorize, is the energy required to remove 1 electron from each atom and 1 mole of gaseous atoms of the element. So that basically means that we have an atom, let's say atom X, and we remove 1 electron from that atom. Now, we already know that 1 mole is going to contain 6.02 times 10 to the 23 atoms. So the ionization energy is how much energy it's required to remove this 1 electron from all 6.02 times 10 to the 23 atoms. And we call that, we can look at the first ionization energy, where we remove 1 electron. The second would be when we remove a second electron. The third, removing a third, and so on and so on. So we can write it out looking like this. So we're going to use this element E. So E just stands for any element. It does not matter what it is. And they are always state symbol of a gas. And we are forming a 1 positive ion with 1 electron being removed. Now, this is regardless of a metal or a non-metal. So we know from GCSE that non-metals tend to form negative ions. It does not matter. Ionization energy always makes positive ions. So the first ionization energy is to go from this atom to a 1 plus ion. The second ionization energy would be to remove a further electron, going from the 1 plus to a 2 plus. Third ionization energy would be to go from a 2 plus and remove another electron to get a 3 plus ion. And we would continue that until we've removed all of the electrons from our element, and it is then whatever charge it would be based on the atomic number. Now, this is a very, very common exam question where it asks you to write out the first ionization energy equation for any electron. What they are looking for is that you know that you have to have it as a positive ion, you have to show the electron, and you must show your state symbols, and it has to be a gas. If you do not write the state symbol, you will lose marks. So we can look at the ionization energy for magnesium. Okay, magnesium, we know, has an atomic number of 12, therefore it contains 12 electrons. So the first ionization energy to get to this magnesium 1 plus is 744 kilojoules per mole. Then the amount of energy it takes to get to the 2 plus is 1,460 kilojoules per mole. To get to a third plus, or a 3 plus magnesium ion, it takes 7,750 kilojoules per mole. So what we notice here is that we get this huge jump in energy in order to remove the third electron from a magnesium. And again, this is a common exam question where we need to be able to explain why we have such a large jump here. And what actually happens when we get this large jump is it's because we're having to break into a full quantum shell, or we are going to a lower energy quantum shell. So for example, if we have magnesium we said was 12. So we're going to have 1s2, 2s2, 2p6, there's 10 electrons, and 3s2. So to get to a 1 plus ion, we're going to remove that one of those s electrons. So I'm going to be left with 3s1. to get to a 2 plus, it's 1s2, 2s2, 2p6. So I've removed both of the 3s electrons. Now to get to a magnesium 3 plus, I need to break into this 2p6 orbital. And now not only is that already a full orbital, it is also much lower in energy in comparison to the 3s. So I would be going to something like that, and that requires a very, very high energy. And we can actually show this pattern using a logarithmic scale against the electron removal, and we can start to see a clear pattern. So when we're looking at sodium, we know back from GCSE that sodium was 281, or if we're looking at A level, it's 1s2, 2s2, 2p6, 3s1. So the energy in order to remove the first electron, which is the 3s, is quite small. And then we get this large jump because now we're having to remove from the 2p. We're going to remove the 2p electrons until this point, and then now we're going to be removing the 2s. But remember, these are all in the same quantum shell, so they have similar energies. But again, we get this big jump now where we're having to remove a 1s electron when I start to remove electrons 10 and 11. So we can actually use the logarithmic scale of the ionization energy to tell us the electronic configuration. Because we can see here that I have got 2 electrons, and then 8, and then 1. So if we look at another way to think about ionization energy, we can define it as the energy of the electron when it is removed, take away the energy of the electron when it is in the orbital. So for example, if I have my atom and I have my orbital here, the ionization energy, the energy when the electron is removed is going to be at a specific energy level when it is no longer attracted to the nucleus. So let's say that energy is here. So we want to take this electron and move it up to the X. And that will make sure that I have no longer got any attraction to my nucleus. So that's the energy of the electron when it is removed. The energy of the electron that's in the orbital is when it is just as it's shown in the diagram when it's that E minus. The ionization energy is the energy required to go from here up to there. So this means that if we have electrons that are in the outer quantum shells, they are going to have a shorter distance between the electron and this point of X. So that's going to require less energy. The closer the electron gets to the nucleus, the further away it is from this point X where there's no longer an attraction. So the outer electrons require less energy in comparison to the electrons in the inner quantum shells. And the ionization energy for any particular electron will depend solely on the energy it has within the orbital. Now, you're not expected to put a number on the energy it has within the orbital. You just need to understand that it has this energy, and we want to take it to a much higher energy so that there's no longer this attraction. So now let's think back to our graph where we had our sodium ionization energies. We saw that we got an increase in the ionization energy as we removed more and more electrons. And we need to be able to explain this. So sodium, remember, is going to be 1s2, 2s2, 2p6, 3s1. So if I draw this out where we have our sodium nucleus, we have our first energy level, our second energy level, and then our third energy level. And we want to get all of these electrons to the point X. So this point X is where there is no attraction for the nucleus. So the electron is completely free from the attraction with the nucleus. And this is where we want to get the electron from the orbital to this, and remember this distance is our ionization energy. So when we have the electrons in the third orbital, the third quantum shell, it's going to be the outermost electron, so it's going to be the closest to this point X. So this is going to have the lowest ionization energy. Okay, in this case we're using IE to explain ionization energy. In an exam, please don't use this term. This is just to make it easier for the slides. Write out the full words, ionization energy. When we move on to the second ionization energy, so this is now wanting to remove an electron from the 2p6 orbital, we have to go from a higher energy orbital to a lower energy orbital. So we're going to a lower energy than this first electron. So then our second ionization energy is going to therefore have to be higher than the first, because the distance between the third to this point X and the second to this point X is larger. So my electron is closer to the nucleus, further away from point X, so the energy needed to take it there is bigger. Now, the more electrons that are removed, the less we're getting repulsion between the electrons and the orbitals. Remember, all electrons are negative, and negatively charged substances are going to repel other negatively charged substances. So once we get this repulsion being removed, that actually increases my ionization energy. When the electrons are paired up, we can take advantage of that because they're removed a little bit easier. As soon as we get to an orbital where it is only one electron, it becomes a bit more challenging. So we get an increase in our ionization energy as we remove more electrons from the second shell. The last electrons 10 and 11, have to be removed from the lowest energy shell, so they require much larger amounts because, again, the distance from the energy shell 1 to point X is much bigger, so again the energy needed to move at that distance becomes larger. Now, electron-electron repulsion is sometimes known as shielding or screening, but this is the term that we prefer at A level. We want to call it electron-electron repulsion. The reason for that is when we say something like shielding, that implies that there's a physical barrier actually shielding something. And that's not the case here. What it actually is it's a repulsion between a negative and negative charge. Remember, like charges don't like to be near each other, they will repel each other. So we're going to use the term electron-electron repulsion. And what this actually does is it raises the energy of the electrons to above what the value would be if there was no repulsion. What does that actually mean? Well, it means if I have one electron versus a doubly filled orbital, so I have two electrons, the energy of these two is going to be slightly higher than the energy of this one because these two electrons will repel each other. So they want to move slightly further away so they're at a slightly higher energy. We also get this shielding or electron-electron repulsion from the inner electrons to the outer electrons. So your electrons in quantum shell 1 and 2 are going to be repelling the electrons that are in energy level 3. So this is a way that we can explain why quantum shell 3 is at a higher energy level than quantum shell 2 and 1. It's because we have this repulsion between the electrons in shell 1 and 2 and the electrons in shell 3. So if we have an electron in an orbital where it's paired with this other electron, it's going to experience this repulsion. So it gives you a slightly lower ionization energy in comparison to when we only have one electron. Okay, and the shielding, as we said, it's not a physical barrier, it is simply a repulsion that affects the energy of an electron. So the main things that affect the energy of an electron, which are then going to affect the ionization energy, we have to look at the orbital in which it exists. So does it exist in what quantum shell? Is it 1, 2, 3, 4, and so on and so on? And we also have to look at the subshell. Is it an S? Is it an P or D? Because these are going to have different energies as well. We also have to take into account the nuclear charge of the atom. So how many protons are there? And we'll talk more about that when we look at topic 2b and we're looking at the trends in ionization energy. So we'll come back to this one. And we also need to look at the repulsion or the shielding experienced by the electrons. So if it's in a higher energy orbital, it's going to have increased repulsion. If it is in a doubly occupied orbital, i.e. it has got a partner, so there are 2 electrons in it, it is also going to experience increased repulsion. And any increased repulsion is going to cause your ionization energy to be lower. So high repulsion gives a lower ionization energy. And again, we will come back and discuss this in topic 2b when we're looking at the trends. Just very briefly going to mention the trends in the ionization energy. As I've said multiple times now, we will go into this detail in topic 2b. As we go across the period, there is an increase in the first ionization energy, and that is because we have more protons in the nucleus, meaning the electrons are going to be more tightly attracted and tightly held to the nucleus. As we go down the group, we see a decrease in the first ionization energy because if we look at group 1, lithium contains 2 quantum shells, sodium contains 3, and potassium contains 4. So we are actually making that outer electron further away from the nucleus, causing the energy to get it to that point X to be lower. So we'll finish off looking at a past paper question. This is from the October 2018 paper. And firstly, we're looking at the electronic configuration of an atom of zinc using our SPD notation. So we want to think about zinc has got an atomic number of 30. So we're going to be using our Aufbau principle and our Hund's rule in order to figure out the electronic configuration. So we have 1s2. We then move to the 2s, that holds a maximum of 2 electrons. We have the 2p, which holds a maximum of 6. So we've placed 10 electrons. So we know we need to keep going. So we move into the 3s, that holds 2. The 3p, that holds 6. Now remember that exception to the Aufbau principle, I want to fill the 4s before the 3d. So I'm going to have 4s 2. So now I've filled in 20 electrons, and we know that the 3D can hold a maximum of 10. So my electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And the mark scheme will allow you to put these 2 in either order. It does not matter. Then we want to be looking at the second ionization energy. So remember, this is when we're going from a 1 plus to a 2 plus. So we've already removed 1 electron, now we're removing a second. And it shows the examples for some elements in period 3, and we want to mark on the grid with a cross the value we would expect for sulfur. And we've said just briefly there that the ionization energy is going to increase across the period. So we're going to have a value somewhere above P, but not too far above. So we're going to put it approximately here. Okay, anywhere between 2,100 and 2,400 would be an acceptable answer. Then we want to have an equation including state symbols for the second ionization energy of aluminium. So remember, this means that we have aluminium 1 plus, and it should always be a gas. And we are then going to an aluminium 2 plus ion, which is a gas, plus 1 electron. You get 1 mark for the equation, 1 mark for the state symbols. Please make sure that you include the state symbols. Then we want to explain why the second ionization energy of aluminium is greater than the second ionization energy of magnesium and that of silicon. So we want to think about where the electrons are coming from. So if we have magnesium, we know that's atomic number 12, aluminium is atomic number 13, and silicon is atomic number 14. So they're all going to have 1s2, 2s2, 2p6. That's not going to change. What is going to change is the 3. So here for magnesium, we are going to be taking, we would have 3s2, aluminium would be 3s2, 3p1, and silicon would be 3s2, 3p2. Now that's if they were all atoms. Because we're looking at the second ionization energy, we've already removed one electron from silicon. We've removed this electron here, and we've removed one electron from the magnesium. So if we're looking at magnesium and aluminium, both for magnesium and aluminium lose an electron from the 3s orbital. But because aluminium has slightly more protons, so aluminium has more protons than the magnesium, that's going to give you an increased attraction between the electrons and the nucleus for the aluminium. So we get an increased attraction. Of course, you would be putting this into much more better sentences than I am. When we're looking at for the silicon, we're saying that for silicon, we remove a 3p electron. And the 3p electron is going to be a higher energy than the 3s. So 3p is a higher energy than the 3s. So it has a lower ionization energy. So this is looking at a comparison in two different ways. It's comparing the s and the p orbitals and what effect that has, and also comparing what happens when we take them from the same orbital but for different elements. So the magnesium and the aluminium, this time we're looking at how many protons they have. And again, we'll come back to this in topic 2b. There is quite an overlap here in these questions. And then predict with a reason which element in period 3 has the highest second ionization energy. Well, we said as we go across the period that we're going to see an increase in our ionization energy. We're thinking about the element with the highest second ionization energy, and the answer is going to be sodium, because the electron is removed from an energy level closest to the nucleus. Because if we think about the second ionization energy for sodium, we've had 1s2, 2s2, 2p6, 3s1. That's for the sodium. When it's the sodium ion, I've already removed that 3s1. So now I'm having to go into the second quantum shell. So although we do see an increase in our ionization energy across the period, that's specific to the first ionization energy. When it's the second, we need to consider, are we breaking into a lower energy orbital compared to what we were for the first ionization energy? And in this case, we are, because for sodium, the electron is removed from the 2p orbital, which is closer to the nucleus than the 3s. So there you can see the mark scheme if you wanted to try those questions on your own, and you can see how the marks break down. That's everything for atomic structure. I would strongly suggest that you do some practice questions, particularly writing out the electronic configuration, and you can find examples in the textbook. You can check in past papers, or of course you can ask your teacher and they'll be more than happy to help you. If you do have any questions, please feel free to leave a comment below, and we hope to see you back soon.